Okay, so we're going to talk about the double angle, power reducing, and half angle formulas. First, we'll start with double angle formulas. So several important identities follow from the sum formulas for sine and cosine and tangent, such as these double angle formulas. So the first one we see here is sine of 2 theta equals 2 sine of theta cosine of theta. The next one we have is cosine of 2 theta equals cosine squared theta minus sine squared theta. And then tangent of 2 theta equals 2 tangent theta all over 1 minus tangent squared of theta. And so let's just show or verify that the first and second identity is equivalent to the right hand side. So let's take, for instance, sine of 2 theta and show it's equal to 2 sine theta cosine theta. And this basically follows from our double angle formula, or our sum formula for sine. So if you recall, sine of alpha plus beta is equal to sine of alpha cosine of beta plus cosine of alpha plus sine or times sine of alpha beta. And so from there, if we could use this formula to verify sine of 2 theta equals 2 sine of theta cosine theta. So for instance, we could start with the left hand side of this identity and show it's equal to the right hand side. And so sine of 2 theta can be written as sine of theta plus theta, right? So that's a sum. So using the sum angle formula here, we know that's going to be just sine of theta cosine of theta plus sine of, or cosine of theta sine of theta. But of course, these are just the same two terms here, right? You would swap them and they're like terms. So therefore, how many do we have? We have 2 sine theta cosine theta. And so that's exactly the right hand side, and we just verified that identity is equivalent. Likewise, we could take the identity cosine of 2 theta equal to cosine squared of theta minus sine squared of theta, and show that this identity is equivalent using the sum of 2 angles for cosine. So cosine of alpha plus beta is going to be cosine alpha cosine beta minus sine of alpha sine of beta. And so that's the sum of 2 angle formula for cosine. So using that identity, we could show this identity here for cosine is equal to cosine squared theta minus sine squared theta. All right, so we'll start with the left hand side. And so cosine of 2 theta is the same as cosine theta plus theta. And so that's equivalent to cosine theta cosine theta minus sine theta sine theta again, which those are the same terms there. So we get cosine theta, which is just cosine squared theta minus sine times sine, so that's sine squared theta. And that's the right hand side of our identity, which is what we wanted to verify. I'll leave the tangent of 2 theta for you guys to verify. So let's see how we could use this. So let's take a look at this example here. If sine theta equals 5/13 and theta lies in quadrant 2, find the exact value of each of the following. All right, so we're actually finding sine of 2 theta. But before we could find sine of 2 theta, we need to make sure we know what kind of cosine of theta is. All right, and so we know that basically we can use the unit circle to help us identify what the sine and cosine is. And so we could imagine that our theta, which lies in quadrant 2, so imagine it here, and it intersects, or its terminal side, theta intersects at that point there, which would have coordinates x and y, but we know sine of that theta is 5/13 if we use the unit circle. So once again, the unit circle states that x squared plus y squared equals 1. And so we know the y coordinate, and therefore we know the x coordinate. Okay. So we're just going to have this equation x squared and then plus y squared, but y squared is 5/13 for this angle, squared equal to 1. So we have x squared plus 25/169 equal to 1. And from this then we could see that x squared is going to be equal to 1 minus 25/169, which tells us that x squared is equal to 144/169. Now x is going to equal the plus or minus the square root of that. So the square root of 144 is going to be 12. The square root of 169 is going to be 13. Now, is x positive or negative? Where in quadrant 2, we know that it's negative, so that means x is equal to negative 12/13. In other words, what we know here is that cosine of this angle theta is equal to negative 12/13. That's the unit circle definition. And so now we could go on and answer question A here, which says that sine of 2 theta, okay, we want to find sine of 2 theta. Okay, so if we want to find sine of 2 theta, we could use the double angle formula that we just derived. And so we know this is going to be 2 times sine of theta cosine of theta. And so 2 times sine of theta, which we know is 5/13, times cosine of theta, which we just figured out to be negative 12/13. Okay, and so we get negative 120/13 times 13, which is 169. Okay, and so sine of 2 theta is negative 120/169. Likewise, we could find cosine of 2 theta. Cosine of 2 theta using the double angle formula that we found. We know that's equivalent to saying cosine squared of theta minus sine squared of theta. So we have negative 12/13 squared minus 5/13 squared. Right, so we get 144/169 minus 25/169. Subtracting that gives us 119/169. All right, so the cosine of 2 theta is 119/169. All right, so now we could find tangent of 2 theta. But before we find tangent of 2 theta, we probably want to find tangent of theta. And we know tangent of theta is just y/x for this particular theta. And we know it lies in quadrant 2. And so it corresponds to y equal to 5/13 over cosine, which is negative 12/13. And so the 13th one, the fraction 1/13 cancels, leaving us with negative 5/12, or excuse me, negative 5/12. All right, so that's not our answer because we're interested in tangent of 2 theta. Okay, so here I'm using the double angle formula, and I'll show you an alternative way to calculate that, just using the quotient identity. But just to illustrate the tangent double angle formula, we know this is 2 tangent of theta over 1 minus tangent of theta, and so we get 2 times negative 5/12 all over 1 minus negative 5/12 squared. And you could fill in the details there, and you could arrive at negative 120 over 119. Okay, so alternatively, we can have done this probably a little bit quicker by using that tangent of theta, 2 theta. It's the same thing as, let me just drag this down over here. It's the same thing as sine of 2 theta over cosine of 2 theta. And so we know we just did those calculations, right? So we have negative 120 over 169, and then divide that by 119 over 169. Okay, and so we can see that when we flip it over, we're going to be left with 120. When we keep the first fraction the same and multiply by the reciprocal, we're left with negative 120 over 119, just like we got in the other formula above. Okay, so quicker is just to use the quotient identity there instead of the double angle formula, especially if you know sine and cosine of the particular angle. Alright, here's another example here. We're asked to find the exact value of 2 tangent of 15 degrees minus 1 minus tangent squared of 15 degrees. Well, we can see that 15, this is basically has the form of our double angle formula, and we can see that basically if you double our angle here, our angle 15, right, that would be 30 degrees, and so this has the form of 2 theta, okay, and so our 2 theta equals 30 degrees, and so we're kind of going backwards. So 2 tangent of 15 degrees over 1 minus tangent squared of 15 degrees is the same thing as just saying tangent of 2 times 15 degrees. Okay, which is just tangent of 30 degrees. And we know from the unit circle that's just 30 degrees is in this quadrant, which corresponds to the special point, if you want, 30 degrees, root 3 over 2 and 1/2. Okay. And so we know that tangent is just y over x, so we'll have 1/2 over root 3 over 2, which is just 1 over root 3, or if you rationalize the denominator, radical 3 over 3. The double angle formula for cosine is often written in the form cosine of 2 theta equals 2 cosine squared of theta minus 1, or cosine of 2 theta equals 1 minus 2 sine squared of theta. So let's go ahead and verify this equivalent identity. So cosine of 2 theta equals 1 minus 2 sine squared of theta. Alright, so to do this here, we'll start with the left-hand side, and we have cosine of 2 theta. So from earlier, we saw that's equivalent to saying cosine squared of theta minus sine squared of theta using the double angle formula for cosine. Okay, so then, notice that this involves a sine squared, and you have 2 of them, and so we could use our Pythagorean identity. Let's say sine squared theta times, or sine squared of theta plus cosine theta equals 1, which shows that cosine squared of theta equals 1 minus sine squared of theta. And so we know we could replace cosine squared of theta with 1 minus sine squared of theta minus sine squared of theta. Alright, so what does that give us? That gives us 1 minus 2 sine squares of theta, and which is exactly what we wanted to show. That's the right-hand side, so we're done. Alright, here's another identity. We're asked to verify the identity that cosine of 3 theta equals 4 cosine cubed theta minus 3 cosine of theta. Alright, so we'll start with the left-hand side, even though it's more simpler. And that's just because we have some formulas that involve, a double angle and a sum of angles. So, for instance, cosine of 3 theta is the same thing as cosine of 2 theta plus theta. Okay, and now we could use the sum angle identity, for cosine, which says this is the same thing as cosine of 2 theta times cosine of theta, and then it switches signs to minus sine of 2 theta times sine of theta. All right. Now, using the double angle formula for cosine of 2 theta, we would get cosine, in the particular one, the one above that we just stated, right? We'll use this one here. And that would give us 2 times cosine squared of theta minus 1 times cosine of theta. Likewise, we're going to use the double angle formula for sine. And sine, we know that gives us 2 sine theta cosine theta times sine of theta here. And so let's go ahead and use some algebra here to simplify this. So distributing the cosine times there, we would get 2 cosine cubed, because you have 2 factors of theta there, times another factor makes it 2 cosine cubed theta. And then, of course, distributing here, we would have minus cosine of theta. Likewise, if we distribute sine of theta to there, and we not distribute, just multiply, there's no sum there, so we'll just have minus 2 sine squared of theta cosine of theta. All right, we're not there just yet, because notice the right hand side of this identity does not involve any cosines, or excuse me, doesn't have any sine. So that means we need to get rid of this sine squared theta, and you once again using pretty much this identity here. Again, right, the Pythagorean identity, we could always write this as sine squared of theta equals 1 minus cosine squared theta. Okay, so we'll substitute that there. So we're left with 2 cosine cube of theta minus cosine of theta minus 2 times 1 minus cosine squared of theta times cosine of theta. And then now, using some algebra, we can distribute and also distribute the 2. But in any case, what do we have left? We're going to have 2 cosine cubed theta minus cosine of theta, and then minus 2 times 1 there times cosine. So we have 2 cosine theta there when you combine that there. And then again, plus negative 2 times a negative cosine squared theta, it would be positive 2 cosine squared theta, but then distribute the cosine theta, that gives us 2 cosine cube of theta. And we actually have some like terms here. So you can see where the 4 is coming. So we're going to have equals 4 cosine cube theta, and then minus 1 cosine theta minus 2 cosine theta is minus 3 cosine theta. And that is the right hand side of that identity, so we're done. Okay, so we have what's called the power reducing formulas, and these can be derived using the double angle formulas. The first one we have is sine squared of theta equals 1 minus cosine of 2 theta over 2. Cosine squared theta equals 1 plus cosine of 2 theta over 2. And then tangent squared theta equals 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. All right, here I'll show you how to derive the first one here. We know cosine of a double angle, in other words, twice an angle, is equal to 1 minus twice sine squared of the angle. That's one of the equivalent forms of the cosine double angle formula. And so if you solve for sine squared of theta, you basically get the identity that's called the power reducing formula. So if we subtract, say, 1 on both sides here, we would have cosine of 2 theta minus 1 equals minus 2 sine squared of theta. And now if you divide both sides by negative 2, the negatives will give you negative and cosine of 2 theta plus 1 over 2, just distributing the negative sign. The right hand side is simply sine squared of theta. And the arrangement here is not how I wrote it up there, but you could see that if you just swap these guys around, you would have 1 minus cosine of 2 theta all over 2, which is exactly what we want. And of course, cosine squared of theta equal to 1 plus cosine theta can be derived using the other version of the cosine double angle formula, where you had 2 cosine squared minus 1 in the formula. All right, tangent squared theta identity here can be derived because we know this is the same thing as cosine, or excuse me, we know that's the tangent squared of theta can be written as sine squared of theta over cosine squared of theta. So if you assume the power reducing formulas on the right here, we know the sine squared could be reduced to 1 minus cosine of 2 theta all over 2, and then that can be divided by cosine squared of theta, which is 1 plus cosine of 2 theta over 2, which leaves you basically the halves cancel out, leaving you with 1 minus cosine of twice the angle all over 1 plus cosine of twice the angle. And that's exactly the right hand side of the double angle form, or excuse me, the squared power reducing formula for tangent. All right, so write an equivalence expression for cosine of x raised to the 4th power that does not contain powers of trigonometric functions greater than 1. All right, so to do this, we're going to use the power reducing formulas. So cosine of x raised to the 4th power can be rewritten as cosine raised to the 2nd power, and then that being raised to the 2nd power. So in other words, we know from properties of exponents that if you have a raised to the n power raised to n power, that's the same thing as a to the n times n power. So we're just using that property there. Now cosine squared of x can be written as 1 plus cosine of twice the angle, so twice x all over 2, and this here would be raised to the 2nd power. So then we have 1 plus cosine of 2x raised to the 2nd power, and then 2 squared is 4. All right, let's go ahead and expand the 1 plus cosine of 2x. Once again, this is just binomial squared, so that's just a squared plus twice a times b plus b squared. Likewise, we have 1 plus 2 times cosine of twice x plus cosine squared of twice x all over 4. All right, so I'm going to go ahead and factor out that 1/4. So we're left with just 1 plus 2 cosine of twice x plus cosine, I'm not sure, let me erase that there, cosine squared of 2x. And then we need to get rid of now the cosine of 2x squared term. In other words, let's reduce the formula as well by applying the same formula. So we have 1 plus 2 times cosine of 2x, and then this is going to be 1 plus cosine of twice the angle this time, but the angle is 2x, so we're going to 2 times 2x, which gives us 4x all over 2. All right, and so we're going to be left with 1/4 times 1 plus 2 cosine of 2x plus 1/2 cosine of 4x. And we no longer have any trig function raised to a power. And in fact, we know we have 1 plus 1/2 there, so that's 3/2. And I'm going to go ahead and distribute. So we would have 1/4 times that 3/2, which would give us 3/8. And then 1/4 times this term here, which would give us 1/2 cosine of 2x. And then 1/4 times that term there to give us 1/8 cosine of 4x. And that's it. That's our example simplified. All right, now we have what's called our half angle formulas. So an alternative form of the power reducing formulas can be derived by replacing theta with alpha over 2 and solving for the trigonometric function on the left hand side of the identity. Okay, so I'll leave that for you to verify. So we have, say, our first half angle formula, which is equal to plus or minus the square root of 1 minus cosine of alpha over 2. cosine of alpha over 2 is equal plus or minus the square root of 1 plus cosine of alpha over 2. And then tangent of alpha over 2 equals plus or minus the square root of 1 minus cosine of alpha over 1 plus cosine of alpha. And you got to determine the sign depending on where the where the angle alpha over 2 lies, and that helps you decide the sign. Okay, so we have to find the exact value of cosine of 112.5 degrees. Okay, so just to note, if we're going to use this double angle formula, so we know that alpha over 2 is equal to 112.5 degrees, so that would say alpha is equal to twice 112.5 degrees, which would give us alpha equal to 225 degrees. Alright, so we know what our alpha is, so then cosine of 112.5 degrees is the same thing as cosine of 225 degrees over 2, which we could use the cosine formula, which says it's equal to plus or minus the square root of 1 plus cosine of 225 degrees all over 2, which is the same thing as plus or minus the square root of 1 plus, well, cosine of 225 degrees would have a reference angle of 45 degrees. And so we know that's the angle where the x and y coordinates would meet, but in quadrant 225, so therefore that would be negative root 2 over 2. Okay. And so that's all over 2. Alright, so let's go ahead and clean that up. Plus or minus the square root of 1 minus root 2. Actually, let me back up a little here. So we have 1 plus negative root 2, so that's 1 minus negative root 2, but 1 can be thought of as 2 over 2. So this is going to be 2 minus root 2 over 2 all over 2. A little messy there. Combine the numerator there. And then, of course, this is the same thing as 2 minus root 2 all over 4, and then take the square root on top and bottom, so we get plus or minus the square root of 2 minus root 2 all over 2, because the square root of 2 minus root 2, you can't simplify that, but over the square root of 4 is just 2. Alright, how do we decide plus or minus? Well, we know that 112 falls between 90 degrees and 180, and cosine there is negative. And therefore, this should be negative 2 minus root 2 over 2. Okay, so the next example, we're actually find the exact value, typo there, exact value of sine of 105. So likewise, alpha over 2 is equal to 105 degrees, so alpha would be twice 105, which would give us 210 degrees. Okay, so we would have sine of sine of 105 degrees, which is equivalent to half of 210 degrees over 2. And so using the formula that we just learned, this is equivalent to plus or minus the square root of 1 minus cosine of our alpha, 210 degrees, all over 2. Now 210 degrees would have a reference angle of 30 degrees, and 210 degrees falls in the second quadrant, so we know that's going to be negative root 3 over 2, I believe. Yeah, negative root 3 over 2 all over 2. Alright, let's manipulate this here. So plus or minus there, we'll decide that sign in a moment. Let's mark that over there. That's the formula there. So we have 1 plus root 2 over 2, but think of 1 as 2 over 2. And so then we have plus root 3 over 2 all over 2. Let me clean that up just a tad there. 2 over 2, and keep in mind that's under the whole, that's everything is under the square root symbol there. Alright, so then we have plus or minus the square root of 2, so we would get 2 plus root 3 all over 2, but then divided by 2, which is like multiplying by 1/2, so we would get 1/4. Alright, so then break up the radical as radical 2 plus root 3 all over radical 4, and so we get radical 2 plus root 3 all over 2, and then we need to decide whether this is positive or negative, but we know that 105 degrees falls in quadrant, so 105 degrees falls between 90 and 180, which is quadrant 2, and so sine there is positive, so it's just that value there. Alright, let's take a look at an identity question here. So here we're asked to verify the identity. Tangent of theta equals to 1 minus cosine of 2 theta all over sine of 2 theta. For this case, we have a lot to work with on the right hand side. Let's go ahead and work with that side. And so we have 1 minus cosine of 2 theta all over sine of 2 theta. Alright, so we're going to go ahead and use the formulas that we just learned for the double angle for cosine. In particular, I'm going to use the 1 minus 2 sine squared of theta for the cosine 2 theta. And then sine of 2 theta, we know that's 2 sine of theta cosine of theta. Alright, so now notice that 1, when you distribute the sign there, minus sign, so you have 1 minus a 1, so that's 0. And then a negative times a negative makes a positive 2 sine squared of theta all over 2 sine theta over cosine theta. And of course you could cancel out a 2 there, and also one factor of sine on top and bottom here as well, so that leaves 1 sine on top, and then over on the bottom we're left with just cosine of theta, which is actually just tangent of theta, which is the left hand side. And so we're done. Alternative half angle formulas for tangent. So tangent can be written as alpha, essentially from what we just seen in this previous identity, if you substitute alpha equal to theta, so if you make a substitution for theta and replace theta with alpha over 2, you could see that's equivalent to this formula here. Okay, tangent of alpha over 2 equals 1 minus cosine of alpha over sine of theta. The next one here, I'll let you verify that yourself. But you essentially want to just show tangent of theta is equal to sine of alpha, or sine. So to show this one here, you want to show tangent of theta is equal to sine of twice theta over 1 plus cosine of twice theta. And then just like we did in the previous exercise to derive that formula. And then make a substitution that theta equals alpha over 2. Alright, let's use this identity to prove this last identity here. And what I notice is that cosecant of alpha minus cotangent of alpha, it's essentially basically probably going to be using one of the identities above here, because we can see that if you look at the one I just circled here, 1 over sine of alpha is cosecant of alpha, and then cosine of alpha over sine of alpha is cotangent. And so basically we have it already there. So we'll start with the left hand side and use that formula that we just derived. And so the left hand side is tangent of alpha over 2. Right, it's equivalent to 1 minus cosine of alpha all over sine of alpha. And of course 1 over sine of alpha plus cosine of alpha all over sine of alpha. And that's exactly what we want. 1 over sine of alpha is just cosecant of alpha, and then cosine over sine is just cotangent, in this case alpha. And that's the right hand side, and that's what we wanted. And we're done. Alright, so that's it for this video.